standard. So this is a standard used widely in healthcare for transfer of X-ray images. Any images, medical images. So similarly, there are some standards like EHR, Electronic Health Record Standard. Uh, so like the standards are there for any medical image communication part. So for imaging part, DICOM standard is a worldwide accepted standard. So I will show you some collab programs how you can perform detect diseases on X-rays by using AI. Some demonstration can also be of the tool which we are working. Also, if time permits, I will take you through. So to start with, so what is medical imaging? We have X-ray images. So basically, if the X-ray rays falls on the human body, we will the bones doesn't allow these X-ray rays to pass through, and we will get these pictures here, as seen here in my slide. And CT scan image is actually a 3D representation of the X-ray images, multiple, maybe if the whole body 3D representation, then we use CT scan. And magnetic resonance imaging or MRI is used to when you want to see smaller parts of human body like ligaments. So many of you may, if somebody has suffered a ligament injury, then uh, you should be pretty that cannot be identified by an X-ray. But so ligaments are very minute parts of the body. So that bones are not visible in X-ray. So that can be found by this magnetic resonance imaging. And another type of imaging techniques is ultrasound imaging. Based on the sound waves reflections, the images will be generated. So these are the different kinds of images that you commonly see in your medical world. So our so what can we do with these images? One is diagnosis, so identification of the nature of the illness or other problem by examination of the symptoms. uh, so if you can identify a illness, maybe cancer, from the input X-ray image, by AI will detect that and tell. Or a prognosis is a guess of an outcome of a treatment. So we are giving certain medication. So after 20 days, this problem will be reduced. So there will be tuberculosis, then in the chest. So that tuberculosis will get reduced. So that can be predicted by AI. Then it is very helpful, right? And longitudinal study means the progress of diseases over the period of time. So suppose I take an X-ray today, then after 3 months, and after 6 months, and after 9 months. So all the X-rays are given to the AI algorithm, and AI algorithm is will say whether the disease is deteriorating or is rapidly increasing. So this kind of studies we use generally AI in medical imaging. So specific to the longitudinal change detection, one example I have shown here. So here we have seeing lung lesions in this red box, and by using AI object detection algorithms, we are able to detect lung lesions on the first image or X-ray image of the patient. And after 3 months, the X-ray image of the patient is again taken. So here we are seeing the lung lesions get reduced. So the disease is getting reduced. And here you can see the as the beginning, the baseline X-ray doesn't have a mass, but after 3 months when they take the X-ray again, we are again seeing a mass here. So these can be detected by using computer assistance interventions, and they will be possible. So suppose a hospital in rural area has maybe 250 plus patients coming, and maybe there is only one radiologist. If we can upload all the 256 X-ray of the patients into the this AI engine, and AI engine can tell that maybe out of five, that only five are abnormal, and others are normal. Then those five patients can be prioritized, right? So there comes the benefit of using such a AI computer aided detection systems. So some of the existing systems like CXR demo, analyze.ai is a tool where we can see effusion, the effusion detection, disease detection region in X-ray is also detected. Similarly, pneumothorax. So pneumothorax disease is in this region, so that is also being detected, and it is also telling a percentage of probability, maybe around 80 percentage probability this disease is present. So that's what AI engine believes. So that also is being told by the today's computer aided chest X-ray detection engines. So coming to CT scans, you will have a 3D image of the lungs. So these are slices of 3D images. So in which you will be able to detect nodules by a bounding box. So that so you can train AI models to detect these nodules. And in cancer microscopic image detection, leukemia detection we can do. So leukemia shells are in different color. So that is another area where AI is predominant. And there is a Apple app for skin cancer detection. So if you just take the photo of the any mark in your hand or something, it will tell whether there is a it's a cancerous or precancerous or malignant. So uh, the AI model in this mobile app, Apple mobile app, is actually trained to detect these conditions uh, from the input image given. So it will tell whether it is low risk, medium risk, or high risk, whether you have to contact the doctor. Is it a cancerous thing or not? So there are applications like nuclear segmentation from the cell images, microscopic images, and also AI is predominant in detecting diabetic retinopathy from your retina images. So these are the abnormal retina images. These are the normal retina images. So abnormal retina images means retina that is damaged due to the diabetics disease. So this can be classified by the AI algorithms. And recent development with AI, we have language models for visual question answering. So along with the image, if you ask a question, so you know ChatGPT, many of you. So along with the images, if you have to ask the question, it will give the answer. So AI model will give the answer. So here this we can ask, do you see cardiomegaly? So cardiomegaly is actually enlargement of heart. So when this question is asked, the AI model is able to detect the size of the heart. If the size of the heart is greater than 50% of the width of the X-ray, then cardiomegaly is present. So it will answer yes. So here there is no cardiomegaly, so it is answering no. But the AI models are now brilliant enough to understand uh, the text you have typed in and uh, answer the queries related to particular image. So this happens to not only X-rays, we can do it for brain, lung CT scan images or brain images, MRI images. Uh, so if there is a lobe enhancement, so what is a lobe? So if there is an enhancement, so all those things, these kind of models, visual questioning answer models for medical imaging can answer. So coming to histopathological images, which is again the microscopic images. So there the challenge is we put a cell inside a slide and put it under the microscope. So it's not that and the if you have done your biology lab, you might have be turning the knob of the microscope to zoom in and zoom out the images. So it's not always. So what you see at a 2 millimeter zoom is not same as that of what you see on a 100 micrometer zoom or 50 micrometer zoom. So the AI algorithm should be brilliant enough to detect the diseases in 2 millimeter zoom as well as on a 100 micrometer zoom. or 50 micrometer zoom. Uh, so that kind of training is required with multiple zoom images for histopathological images. And even in histopathological images, there are language models for visual question answering being developed. So if a question is related to your microscopic cell image, then the AI models are right now are can answer them, whether it is an yes or no question or some sentence question or two word question. It is currently able to answer. There are models being generated developed for that. And there is something called as medical encoding of the images. So for compression purposes, we can use auto encoders to compress encode the image and store it to a small size image, and later reconstruct the image using another neural network. So these are called as encoder decoder auto encoder networks. So that is also used for reducing the storage size. uh, these are the different applications we discussed for medical imaging. So coming specific to uh, chest X-ray imaging, we need to understand how an image is represented in the computer, and in what way this uh, algorithms work. So if you are very new to computer vision, you might understand how the image will be represented in the uh, by the computer. So generally image is represented in the form of a matrix. So this kind of an image will be generally 256 cross 256 matrix. So right now for representation easiness, I'm using an 8 cross 8 matrix. Uh, and each element in the matrix will be having, if it is a grayscale image or black and white image, we in layman words I can say it is a black and white image. So the grayscale image, each pixel in this 8 cross 8 matrix will have a value between 0 and 255. And 0 means it is a completely black pixel region, and 255 means it is a completely white pixel region in the image. So to make it more clear, if you want to make the center region of this image white, then I have to make these pixels 255. uh, so programmatically, if you look at it for this 8 cross 8 matrix, I values varies from 0 to 8, and j varies from 0 to 8. And if it j is greater than 2 and I is less than equal to 4, so the index is 0, 1, 2, 3, 4, right there for this matrix. So if the I is greater than 2 and I is less than 4, and j is greater than 2 and j is less than 4, which means this set of boxes in the matrix, if I am making it as 255, then this region will become 255 because 255 represents white pixels. So this is a simple way to draw a white square on any input image, that is changing the pixel values to 255, 255, 255, 255, 255 for the region representing those white region in the matrix. So this is all I talked about grayscale images or black and white images. Uh, Whereas for the color image, we will have three matrices: red matrix, green matrix, and blue matrix. And combination of these three colors will form your three matrix values will actually form your color image. And uh, so red matrix will have a value varying between 0 to 255. Green matrix will also have a values varies between 0 to 255, and blue matrix will have all the values varying between 0 to 255. When you combine these three matrices, you get different colors in your image. So color image, we require three matrices to represent that image, whereas black and white image represent only one matrix. So before the deep learning or artificial era, uh, we used many pre-processing techniques to detect the anomalies from input image. So one such method is called as thresholding. So if you so I am doing thresholding with threshold value th equal to 35. So if you have an input matrix like this, and all threshold value equal to 35 means any number less than 35 in this input matrix will be converted to 0 in the output matrix. So that's why you see these red numbers 21, 30, 22, 3, etc., which are less than 35 in the input matrix becomes 0, 0, 0, 0, 0 in the output matrix. And any value which is greater than 35 in the input matrix will become 255 in the output matrix. So that's what you see here, 255, a lot of 255. So in short, the output matrix will only have 0 and 255 uh, after thresholding. So this is an input image, which is a grayscale image. So which has pure black and pure white pixels and intermediate color pixels. But when you convert to a do binary thresholding, and we'll get a binary image which has only pure black pixels, that is zeros, and pure white pixels, that is 255. And in this image you can extract the disease regions more clearly. So this was one of the techniques which used before the deep learning era or AI era. So several such basic image processing techniques like eroding and dilation, canny edge detection, Sobel edge detection, uh, were used. So edge detection methods were used to detect disease in the input images in the pre-deep learning and artificial intelligence era. So coming specific to, so this was a very intro about medical image processing techniques, which were earlier used in the pre-deep learning era. So we're coming specific to the X-ray medical imaging, the things you have to concentrate when you build an AI engine. So first you have to check whether it is a valid X-ray image, valid image. So it should be either in JPEG or PNG format, or it should be a DICOM format image, which is the .dcm extension or .diocom extension. So then only we should accept it. So after uploading, you have to check whether it is a valid X-ray image. So it cannot be a person image, or so for that purpose, you have to use some measure methods like structural similarity index. So you have to compare the input image with a X-ray image and find out whether it is similar to an X-ray image. If not, you have to say it is not a valid image. A person image, if you upload, it should not be accepted by the AI engine, right? So necessary precaution should be taken. And distorted image, so maybe if the person has moved when the X-ray image is taken, then you will get a distorted image. So these kind of images should be rejected when you upload the image itself. So otherwise XAI engine will give a fault output. So it is recommended to uh, remove these distorted images as well. uh, So there are different types of X-ray images: posterior anterior chest X-ray images, anterior posterior chest X-ray images, supine view chest X-ray images, or lateral view chest X-ray images. So in posterior anterior chest X-ray images will be taken in this person in this position, where X-ray light will fall on the back side of the person, and so you will get the film like this. But in other methods like lateral images, X-rays, the X-ray beam will fall on the left side of the person standing like this, and you will get a lateral X-ray like this. And there are other positions like lordotic X-ray position, or AP supine X-ray position, and anterior posterior position of a taking X-ray image, where when the X-ray rays falls on the front chest part of the body of the patient. So AP supine images are usually taken when patient is in critical condition. So usually sometimes there may be some tripwires or some ECG wires which is actually falling over the top of the X-ray. So your AI algorithm should be intelligent enough to detect these wires and support devices and not as any specific diseases. So that should be taken care while you are training your AI machine learning algorithm. So, as I said, DICOM is a digital standard, digital imaging and communications in mission in medicine, which is a standard for representing medical imaging in the healthcare sector. So, most of the current X-ray machines uses picture archiving and communication system. It is a computer means of replacing the roles of conventional radiological films. So earlier we were actually using radiological films and its color changes when X-rays fall on them. So right now we have digital X-ray machines which will actually give you the X-ray image in your computer. So using picture archiving and communication systems, you can softwares you can actually view them in the computer itself. So earlier if we were having these films, there is no medical digital images. Uh, so as I said, the data will be stored in DICOM format. So DICOM format, along with the image, there will be some metadata information which will be stored along with a DICOM tag. So DICOM tag is a number like this 0x0010, which is a key, and there will be a keyword associated with each tag like patient name, and there will be a value. So here the value is patient's OP number only they have given because of the uh, data security purpose. They won't reveal the name. Uh, so DICOM is actually a format where the parameters can be represented in the form of tag, keyword, and value pairs. Uh, Parameters related to X-ray can be represented in the form of tag, uh, keyword, and value pairs. So as computer engineers, we will be more interested in understanding how how we can access these DICOM images by using Python program. So we'll just move on to a Colab tutorial for this. We'll see that and then come back to the presentation so that it is more clear. So hope my screen is visible. So to access the DICOM standard images, you have to usually use this library called uh, PyDICOM, Python library, so which you can install by pip install PyDICOM, and then you have to import this uh, PyDICOM library in your Python program to really use it. So I have my DICOM files, image file in my Google Drive. So that's why it's asking me permission to connect to the Google Drive. And so once I connect to the Google Drive, uh, I can read the DICOM image. So here my DICOM image is present inside my drive DICOM sample folder. Inside that there is 0000055.dcm DICOM file, and this will be in DICOM format. So DICOM format means does not, this file does not have only the image but also the patient information and the machine information. So this image is actually a CT scan image, not X-ray image. So which you can see from this PyDICOM data metadata, that is 00321060 is the tag, and requested procedure description is CT scan, and there are other metadata information. So this was taken by using a Siemens machine, and uh, also you have the informations like uh, so all these information related to the uh, the image will be stored in this DCM underscore data variable and in the form of tag value pairs. and the actual image part will be in pixel array. Sorry. So one of the tags pixel array. So that is why DCM dot data dot pixel array I am using to represent the image part, because we are as image processing engineers looking to uh, do deep learning identification. I am interested in this pixel array, which is the metrics which I defined earlier. So generally, this is a matrix which is used for representing the image. So we are interested in pixel array, which contains this matrix. And so I am after, so CT scan images are 3D images. So when I run this code, I will actually see the axial slice of a CT scan image. Uh, so it is actually one of the slices of the 3D CT scan image you can see here. And you can access the patient name by using DCM data dot patient name, or using the tag values as well. So this is patient name is a keyword, or you can use the tag to access the patient name. So as I said, DICOM data is generally of this format: DICOM tag, keyword, value, element value. So you can either use tag or keyword to actually access the DICOM data. So you can see here, uh, when I run this cell, I can get keyword is study ID, name is patient's name, value representation is given, elements value is this OP number of that patient, like that. You can get the all this information, not only the image but also all other information from the uh, of the patient in DICOM file. So XDICOM is dot DICOM is here the extension of the file is DICOM. So earlier file you saw the extension was DCM. So there are DICOM files with DCM extension and DICOM extension. So that's what. Uh, and this is actually an X-ray image, not. Uh, so actually, I am seeing an inverted image. So inverted X-ray image here. So inverted X-ray images means all the white pixels in the X-ray images are converted to black, and all the black pixels in X-ray images are converted to white. So this is generally used by doctors to identify diseases in case it is not properly disease is not properly visible in the input image. So uh, this inverted X-ray images also can be plotted by using these libraries, matplotlib, and original X-ray images can also be plotted for the DICOM images using this uh, PyDICOM library. So the more interesting, there is another library called ImageTote also in Colab Python, which you can use for actually uh, working on 3D CT scan images. So let's see how it is different from the PyDICOM library. So here you have to import image IO, and I am again connecting to my Google Drive to access the DICOM files. So instead of DCM read in PyDICOM library, here we use imread, image.io.imread function. And I am reading this CT scan image 000055.dcm. And you can see the im.meta will have the metadata associated with the DICOM file. To steady resolution CTs, just WC manufacturer Siemens. And pixel data variable will actually have the metrics, which is actually representing the image of the uh, CT scan. So here we can see the axial slice. So generally CT scan images, as I said, is 3D image. This slice which I shown you as axial slice is actually a slice along the traverse plane. So in short, I can how we can represent is like if you are taking a bread piece and cutting it into smaller pieces, maybe 10 piece or 15 piece. One side of the bread what you see is the traverse plane, so which is what you have seen in the uh, previous uh, so this axial slice is along the traverse plane. So that is one side of the bread if you cut along this 3D image of the human uh, along the traverse plane. So you usually I have seen CT scan is taken, then patient's whole body goes inside into a CT machine, and X-ray rays fall over the patient to take the entire 3D image of the patient. So we actually make slices of that 3D image, which is like a bread, along traverse plane, coronal plane, or sagittal plane to get the different CT scan images. So it's not in one image you have to detect a disease. You have to detect all the diseases in all the slices along the human body to actually make the CT scan to detect CT scan diseases. So I am now loading another using image old read function. Earlier I showed you IM read. There is ODM read function. Using that, I can read the entire 3D image from 0000065.dcm. And if I analyze the image, shape of the image, I can see that along the axial plane there are 99 slices, and around the coronal plane there are 512 slices, and around the sagittal plane there are 512 slices, which means that this CT scan image of this human body along the traverse plane is cut 99 times, and along coronal plane or sagittal plane it is cut 512 times to get 512 different images. So if you look at the aspect ratio, you can programmatically calculate here. So the axial plane, the slice thickness is 3 mm. Of course, it will be higher because there are only 99 slices. For coronal plane and sagittal plane, the size slice thickness is 0.56 mm. Because there are more number of slices, of course, this sampling will be, so thickness of the slice will be around 0.56 only. And this is the aspect ratio, axial plane 1, and coronal plane and sagittal plane aspect ratio is 5.3. So it's a proportion of the thickness, proportion of that. And you can, using this image volume library, you'll be able to view different slices of along axial plane, coronal plane, and sagittal plane. So sagittal plane. So I think you can now visualize why this shape is, because sagittal plane and coronal plane are slices along this plane and this plane. So that's why you see a different type of image in coronal and sagittal plane. So now coming more, so there is not only one such slice. I said there are multiple slices. So you can build widgets to view different slices of the images along the axial plane or traversal plane. So this is the 50th slice. Generally, we take the center slice if you don't have much computational power, but otherwise we have to look into all the slices. So I'm just moving this slider. You can see how the slices vary. So this is actually you are seeing the slice along the length of the human body. So how the slices vary along the axial plane or traversal plane. So uh, it's not only that I can vary it along the axial plane or traversal plane, I can also vary it along coronal plane, sagittal plane, and axial plane. So I'm right now seeing the 49 slice of axial plane, coronal plane 255 slice, and sagittal plane 100 slice. So if I vary coronal plane, you can see this picture is changing. Now I'm looking at the 414 slice. Actually, I have 512 slices, right? So similarly, I can move to the other side as well. So these are different slices, and each slice is of different shape. You can visualize along the coronal plane. Along sagittal plane, I can move to a different slice. You will see a totally different picture. Uh, so if you go to 62 slice, you will see a different picture. If you go to 207 slice, you will see a different picture. So the idea I want to convey is that AI has to detect not only if it is a 3D image like CT scan or MRI, both are 3D images. You have to detect the diseases not only in one image but also along all these slices to tell whether a person is normal or abnormal. And you can use image IO for library or PyDICOM library. Generally, the images will be stored in DICOM format in any hospital X-ray machine output. You will also get JPEG or PNG images nowadays. With digital X-ray in a lot of facilities, softwares have come up with where the X-ray image can be exported as JPEG and PNG images. But ideally, for all the medical image communications, the recommended world standard is DICOM format for any hospital information system. Uh, Let me come back to the slides. I will come back to. So they now to train any machine learning model, we need to have data, and there are several such data sets which are openly available for training X-ray AI algorithms. So what is data set? Data set will be for as far as medical imaging X-ray is concerned, you have an X-ray image along with the disease name associated with that X-ray. So like analytics, cardiomegaly, effusion, infiltration, mass, nodule, pneumonia, pneumothorax, and so these are the different disease manifestations, which is comes as labels along with the input chest X-ray image. And so National Institute of Health USA is a hospital where chest X-ray images with for 8 different diseases are already data set is they have released. So later they released a 14 disease manifestation data set. This is commonly used for machine learning problems in and but doctors were using ABCDEF diagnosis method most of the time. Like first it will check for the airways, then it will check for the bones which are white, and then it will check for the cardiac region whether there is an enlargement or not. Then effusion. Then pleura. So pleura is somewhere around this. So this was a method for abnormalities in each of these body region doctors were looking at. But missions we have to train with the images which are abnormal. So later they become neural networks become brilliant enough to understand these diseases. So that's a methodology we follow for in machine learning algorithms. And it's not only the chest X-ray dataset, NIH dataset, which has 14 diseases and around 1,23,000 images. There are ChestNet Stanford datasets, which is actually a better version of NIH dataset as well. And there is 2,24,316 images with of 65,240 patients, more with the 14 diseases being labeled. So many of these data sets where since there are so many large number of images, doctors are finding it difficult to label. So in fact, NIH dataset is the labels itself is extracted by using LSTM language processing models, which will from a website of this hospital, which is actually storing the X-ray data along with the findings marked by the doctors. So coming to the another dataset is Mimic CSR dataset, which has 3,77,110 images. So with for around, but it is again some proprietary. I think some people who have completed some radiology or some course prescribed by this physionet only can access this. Patchet dataset has 67,000 images, but it has a wide variety of diseases, maybe 52 diseases or 54 diseases, disease manifestations. So that's why if you want to try your algorithm to detect multiple diseases, I recommend to go for patches dataset. The latest dataset among them is WinDRCXR dataset, which is a more recent one around 2021 20, and it has DICOM format images itself, and the size of these datasets are very large. So I think this ChestX-Ray dataset is 110 GB or something, but you have a stripped down version of 11 GB as well for experiments. Even this just X-ray NIH dataset is 40 GB dataset. So you need to have a GPU graphical processing unit card to actually perform training on these many of these large datasets to detect diseases. So as any data analytics problem you might have faced here also, you need to collect the data. Then you have to perform necessary cleaning and before analyzing or interpreting any results. So that's why I will take you to again to another collab where the data the data cleansing is being discussed for NIH dataset. So NIH dataset, as I said, is having 1,23,000 images, and it's very big dataset. So right now I am since Colab doesn't support that many big number of images. Since I'm using a free version, I'll stick to the small subset of 1,000 images for the demonstration purpose in interest of time. And I have a folder NIH in my Google Drive in which all the images are present, X-ray images are present, and also I have a file called train hyphen small dot csv, which has a image file name and the corresponding disease names, whether present or not marked by 0 or 1, 0 means disease is absent in this X-ray image. 1 means disease is present in this X-ray image. So this 0002985 underscore 001 dot png has analytics disease. So that's why it is marked 1 here in this column. So can I close this? Can device? Okay, again it's coming up. So, okay, so here I have also this.
போட்டு நீட்டா எழுதி வச்சுக்கோ ரிவிஷனுக்கு இதெல்லாம் தேவை இன்னொரு வாட்டி போட்டுன்னு இருக்க முடியாது அதனால சர்ச் பண்ணிக்கோங்க Sir. Hari Krishnan sir.
Okay, it's muted. Okay. So image which I have used is given here. The image names, the PNG files, and patient IDs are given here, and disease names are given here. Disease manifestation names, and whether the image has a particular disease, that is marked by a 1. So that is a structure of this label CSV file. So I also have these images in my Google Drive folder and Edge. So if I go inside my Google Drive folder and Edges, I think you can see there are so many X-ray images. So these names only I have listed out in my CSV file, and the associated diseases along with. So now I have to look at these. So I am using the library pandas pd.read underscore CSV function to actually load this CSV file and save it in train underscore df. And so train underscore df.info will give me information regarding each of disease. So what are the columns of the this CSV file, and how many entries are there for each column. So there are 1,000 rows for each column. And if I run this, I can see that there are 1,000 patient IDs, but out of them unique are 928, which means there are 928 patients. For some of the patients, I have multiple X-rays. So that's why unique patient IDs are 928. And I can so these are the disease names: pneumothorax, pneumonia, pleural thickening. So I have also patient ID coming in the column, so I have to remove them. So that's what I'm doing here: columns dot remove image, columns dot remove patient ID. So then I'll get the final 14 columns, which are 14 different disease manifestations uh, associated with the chest X-ray given in the data set. So no findings is for the label that is given for normal chest X-ray. So if you look at all the abnormal chest X-rays, then you of the 1,000 chest X-rays, you can see that 106 are athletics disease, 20 are cardiomegaly, 33 are disease manifestation consolidation, 16 is edema, and class of fusion is 128, and emphysema is 13, fibrosis is 14. So you will not get most of the time equal number of disease images. So this is a common problem for any medical image problem, because we don't have equal number of patients for all the diseases. So some of the diseases like hernia has only two samples available, and some other diseases are we have 106 sample, 175 sample, etc. Filtration has one sample. So this is one of the common challenge when you are training a machine deep learning algorithm. If one specific disease has more number of samples in the training data set, then the model will be biased towards that particular disease. So during the testing phase, it is likely to predict more number of times infiltration than other diseases, because more number of samples were used during the training process. So in order to avoid that, there are methods like you have to use a weighted loss function or focal loss function for training your deep learning algorithm. So you can refer what is a weighted local weight function. So weighted local function means if the number of samples is less, like hernia has only two samples, then we need to give more weightage while training the deep learning algorithm. Uh, so I can plot random images from the dataset just for understanding. So these are the different images in the dataset. So some of them are normal, like some of them are abnormal. So with support devices, all those things present. So here a tube is put over his chest. So like the different images you can see. So your objective will be to actually find out whether the X-ray is normal or abnormal and predict the disease manifestation associated with the X-ray images. And so each image is here 1024 cross 1024 pixels. So the metric size is 1024 cross 1024, not 8 cross 8 originally for an NIH data set. And so in order to program a machine learning algorithm, generally we use libraries like TensorFlow or PyTorch. So in TensorFlow, you can import the image data by using image data generator function, and uh, you can so here I am using that function to load all those images using the TensorFlow. So that's it. I'll come back to the presentation slides. So after you have inserted the uh, uh, all these images, sorry. So after you have yeah. So after you have inserted all these images to the machine learning algorithm, the main problem you will experience is you have to use a neural network to train the machine learning algorithm, and that neural network is how does a neural network work, that you need to understand. So for that purpose, I am just quickly going into artificial neural network. So artificial neural network concepts came early 1980s or 60s itself. It is there. So it came from inspired by the human brain neurons. So these are the neurons in human body that has human brain where it has a nucleus and cell body as well as axons. So axons will connect one neuron to another neighboring neuron via uh, a synapses one. Uh, so basically it works by electrical signals. So if I pinch your hand, then uh, how you will feel the pain. So how the pain is felt because some electrical signals pass from your hand to the brain, from one neuron to another neuron to another neuron to another neuron to a particular point in your brain where uh, the brain can sense the uh, pain feeling. So this communication from one neuron to neighboring neuron takes place only if the electrical signal amplitude is above a particular threshold. So if the amplitude is above 50, then neighboring neuron gets fired. If it is less than 50, then neighboring neuron does not get fired. So this is how the human brain neuron works. And mathematicians to try to actually imitate this concept. So they made an artificial neuron where x0, x1, x2, etc. are the inputs for the neuron, and w0, w1, w2, etc. are called as the weights of the neuron. And we take sigma wi xi plus b is a constant called bias. And if it is greater than some value threshold, then the neighboring neuron gets fired. If it is less than some threshold, then neighboring neuron gets fired. So to visualize a mathematical neural network, let's see this picture where the input is 10, 6, 16 and weights are W1.5, W2.5 and WN 0.25. So if I apply this concepts of sigma WI so this will be 10 into zero point 0.5 plus 6 into zero point 0.5 plus 16 into 0.025 equal to 12, or output so output is 12. So if it is greater than the threshold 10, then the neighboring neuron gets fired. So that's how they made this mathematical model imitating the human brain neuron. And so this is one such neuron. So if it is if I can have multiple such neurons connected to each other, then I can make an artificial neural network. So this neural network has three neurons in the input layer, four neurons in the hidden layer, and two neurons in the output layer. So generally, output neurons will predict the probability. So suppose we are doing a classification problem to find out whether X-ray is normal or abnormal. So output neuron will this neuron will predict the probability of normal, and this neuron will predict the probability of abnormal, provided the input X-ray image matrix is provided to the input neurons. So that's how neural network works. So suppose I have see three values x1, x2, and x3 of these input metrics, and output normal X-ray or abnormal X-ray being zero representing normal and one representing abnormal uh, as the labels or the expected outcomes of this machine learning training algorithm. So I can design a neural network with the matrix values x1, x2, x3, etc., xn in the matrix, and we will randomly first initialize the weights associated with each of these connections wj11, wj12, wj13, etc. In each layer of the neural network. And the final outcome, as I said, we'll get a probability here as output of the output neuron. So when I first apply this input of this first row of your my data set, 1, 2.4, 1.3, 1.6, actually I am getting an output after multiplication with the weight summation sigma wxi plus bias. All those calculations, if I do at each of these neuron and at the output layer, I will get a value of zero point 0.7. So zero point 0.7 is the output given by the neural network, but the expected outcome was 0. because this is a normal X-ray, I expect the output to be 0. So what I will do, I will tweak the values associated with each of these connections. I will tweak the values associated with each of these weights, and finally, I will. So error I will calculate first. So error is 0.7 minus you get an output 0. Uh, that error will be minimized. So error is minimized means instead of 0.7 I should get 0. So how we can minimize this error? In that way we have to adjust the weights associated with each of these connections. Uh, so because we are taking sigma x, xi wi, so when we adjust by adjusting the values of weights we can adjust the output. Yeah. So after that, I can apply the second row for input 1.5 to 3.6, and my expected outcome is 1. So each time when I apply this input, I will get, after all the calculation, I will get an output value 0.9, and my expected outcome was 1. But the output I obtained is 0.9. So when I calculate the error, I will get an error 0.9 minus 1 minus 0.1. So again, I don't get a value error 0. So my objective is to get me a 0 error, right? So I'll again adjust my weights associated with my connections. Uh, then again I'll go to the third row. So when each this process weight adjustment happens, so each time when the weight gets adjusted, you will see that we are actually building a neural network which can actually separate out the normal X-ray data points and the abnormal X-ray data points. So the neural network is actually calculating a line which can minimize the error. Minimizing the error means finally a line that can separate the normal X-ray input data points and abnormal input X-ray data points accurately. So that's our objective. So many times we get a neural network of 95% accuracy, which means there may be a some error which we are not able to classify for the input data set. So, uh, so this process is called as training of a neural network. So training means we are adjusting the weights in such a way that the error is minimized. So each time we will adjust the weight W old with the value W delta. So what value is should be W delta by what factor I should actually reduce the weight, the old weight to get the new weight which has less error. So you might have studied in your mathematics classes how d by dw sorry d minima and maxima you might have studied. So where you'll use d by differentiate the dx by dy and calculate x with respect to y. Some calculations you might do to minimize find out the minima. So same principle is applied here. So here we will calculate d by dw, so the value of error for which the weight is value of weight for which the error is minimum, d by dw. So that is what the so please refer to your old max class maximum minima problems to understand it better. Uh, so output of neuron can be generally a threshold for binary classification problem. Binary classification problem is means there are only two classes, normal or and abnormal. Two classes. For example, normal and abnormal in the case of X-ray. But if you are classifying it with 14 diseases, then it is not a binary classification problem. So in the binary classification problem, we can use a threshold. If it is greater than output value is greater than 10, then it is normal. If it is less than 10, then it is abnormal. So something like that, you can design your neural network. And for a simple neural network, there is a derivation by which it is proved that we should adjust the weights by error into input into output into 1 minus output for it. So I'm not going into that derivation part. So coming to deep learning, so there was neural network you know, back in 1980s itself. 1960s itself, in fact, neural network was there, and it can be used for various classification problems to classify normal, abnormal, and etc. Earlier, they used feature extraction methods and machine learning algorithms like support vector machine, random walk, forest, etc. to actually classify artificial neural networks to classify these kind of problems, different disease manifestations or normal, abnormal problems. But with the advent of GPU, the computational power increased. So GPU means graphical processor unit. Many of you might be using that for your gaming in your desktops or laptops. So these graphical processing units have cores. So generally, your CPU cores comes with code for 8-core processor, like that you see where there are 8 cores. But GPUs, NVIDIA GPUs like P5000 has 2000 cores. So 2000 parallel multiplication or addition operations can be performed at a time. So how that helped solving these image processing problem is that if instead of 8 cores performing 8 additional multiplication application, 2000 multiplication addition applications are related to 1024 cross 1024 input image can be performed in parallel, and this helped to the computer's ability to increase the number of layers in the neural network. So I have shown you a 3-layer neural network, 1 layer, 2-layer, 3-layer neural network. So with the advent of GPUs, there are 121-layer neural network, 220 neural network, like the deeper neural networks came into picture, which can so those number of multiplications and additions were possible parallelly, and that led to the increase in accuracy of many of the machine learning models. So one such incident was that went to the breakthrough was the origin of AlexNet. So there is a fellow called Google Alex who worked in Google, who discovered this AlexNet architecture, neural network architectures, and he found that the accuracy of the model is 15% better than the previous models which existed in the as a state of the art. It became like a revolution after 2008 that many people started using deep learning instead of artificial neural networks because there is a high percentage of increase in the accuracy, and generally the deep learning was successful for speech recognition problems, natural language processing problems, and image processing problems. So I will be focusing more on image processing problem as this is an X-ray class. So the problem that can be solved by using deep learning image processing problems, we use convolutional neural network. So generally for natural language processing problems and speech recognition problems, we use neural networks called long short-term neural networks or recurrent neural networks. And programming tools like Piano, Cafe, TensorFlow, Keras, PyTorch, all of these were used to actually program and build these neural networks. Even if you don't have to write all the mathematical equations, these tools support frameworks to build each neuron much easier than writing the entire mathematical equations associated with the multiplications. Yeah. So, as I said, many applications like handwriting recognition, natural understanding, etc., becomes much more accurate. So, one such data, there was a data set called ImageNet released during that time with 1,000 different objects names. Here we have the candle image, oyster image, cannon image, spiderweb image. All those images were present along the labels. So 1,000 such objects like candle, oyster, lizard, stocking, mushroom, strawberry, etc. were they were labeled in the images. So there were, I think, almost 3 lakhs plus images. And AlexNet, which was designed by Alex in Google, who used this image data set to improve the accuracy for up to 15%. And it took 2 weeks for him to do the neural network training process. That is a process which we earlier saw adjusting the weights. So in multiple GPU enabled computers in a multi-processor system. We did this experiment. But right now we have more NVIDIA GPU cards, which comes with this many number of cores in single machine itself. Or you can use Amazon services for doing GPU services for doing such kind of deep learning model trainings as well. So convolutional neural network is just like artificial neural network, but here in the single neuron in a convolutional neural network has convolution layer, pooling layer, and normalization layer. So in fact, the combination of convolution layer plus pooling layer plus normalization layer becomes a single neuron. So if you have an input weight image of 3 cross 3 matrix, and there will be weights will be actually in the form of matrix. So here I have a 2 cross 2 matrix. So the input image every 2 cross 2 is multiplied with the weight matrix. So 10 into 0.25 plus 9 into 1 plus 6 into 0.5, 16 into 0 becomes 14.5. That is written in the output matrix of the code. So this process is called a convolution process of adding each element of the image to its local neighbors weighted by the kernel. So weight matrix is also called as kernel. So here first we have considered this 2 cross 2 of this 3 cross 3 input matrix. Next I have considered this 2 cross 2 of this input 3 cross 3 matrix. So 9 into 0.25 plus 4 into 1 plus 16 into 0.5 plus 12 into 0. I get 14.25. And then again I have to consider this 2 cross 2 of this 3 cross 3 matrix. 6 into 0.25 plus 16 into 1 plus 8 into 0.5 plus 4 into 0. I get 21.5. Again, I'll consider this for 2 cross 2 matrix. 16 into 0.25 plus 12 into 1 plus 4 into 0.5 plus 8 into 0. I'll get 18. So I will get an output matrix of size 2 cross 2 after performing the convolution operation. So there are two terms called as striding and zero padding. So striding, so here I have my input matrix. It's not 3 cross 3 always. Now I have an 8 cross 8 input matrix and a 3 cross 3 weight matrix. And I can perform this operation of convolution on first 3 cross 3, then this 3 cross 3, then this 3 cross 3. Then they call stride as 1. But if you have stride as 2, I'll first to perform convolution operation on this 3 cross 3. Then I'll skip two columns, this, and then perform next convolution operation on this 3 cross 3. Then I'll perform convolution operation on this 3 cross 3. So I'll skip two columns. So if stride equal to 2, if stride equal to 3, I'll skip three columns. So first I will perform this convolution operation on this 3 cross 3. Then I will perform convolution operation on this 3 cross 3. So that's the idea. Stride tells how many columns to skip on the convolution operation, and zero padding is a concept where I can append zeros to the all the four borders of this input matrix. So this is done in order to do a convolution like this. So that the information is not lost. So I can do zero padding. If zero padding equal to 1 means all the four sides of the input matrix, I will append the zero. Four columns will get appended at the four sides of the input matrix. And then that will be provided as input for the convolution operation. So I said convolution neural network has convolution layer, max pooling layer, and normalization layer. The second layer is max pooling layer. So max pooling operation, what it does is out of the every 2 cross 2 input of the input matrix, I'll select the largest value. So here I have 1, 0, 4, 6. Out of that, 6 is the largest value. And so hope my slides are okay. So here max pooling layer I have 1046, so maximum is 6. Then out of this 2 cross 2 2368 maximum value is 8. Out of this 2 cross 2 3112 maximum value is 3. Out of this 2 cross 2 1240 maximum value is 4. So you will get a 2 cross 2 matrix as output of the 4 cross 4 matrix in a max pooling operation. And normalization operation, I will add, I'll take one number as the numerator for a 2 cross 2 matrix and divide it by sum of all other numbers, 2 plus 4 plus 1 plus 3. So 2 by 2 plus 4 plus 1 plus 3, 4 by 2 plus 4 plus 1 plus 3, 1 by 2 plus 4 plus 1 plus 3, which is actually 10. That's why I've done 10. And I'm 3 by 10. So finally, I'll have all the numbers between 0 and 1 when I perform this normalization operation. Or each of these number will be between 0 and 1. So that will be better for multiplication operation. So, as I said, AlexNet was a first neural network. This is architecture of AlexNet, where the input image is 227 cross 227 cross 3, and the kernel, the weight matrix size is 11 cross 11 weight matrix, and they have used a stride of 4. So, not only one matrix, they have used 11 cross 11, 96 such metrics they have used. So that's why the output size is a 96 dimensional. So 227 cross 227 cross 3 input matrix, when it is applied with a 11 cross 11 matrix for by convolution operation, you got a 55 cross 55 matrix. So since there are 11 cross 11 96 matrices, I got 55 cross 96 as my first layer neuron output. So after a convolution operation, there is a new max pooling operation. We saw max pooling where maximum of the delivery 2 cross 2 is taken. So that's why 50 cross 5 cross becomes half, 27 cross 25, 27 cross 27, and after the max pooling operation. So several, one convolution operation, one max pooling operation, then another convolution operation, another max pooling operation, another convolution operation, another convolution operation, then again max pooling operation. And after that, we have a fully connected network, which is earlier discussed artificial neural network. So output of this neural network for 3D neural network is given by fully connected artificial neural network, which we discussed earlier slides, the three-layer neural network. And with an output layer of 1,000 neurons. So each of these 1,000 neurons will tell the probability of whether a car is present in the input image, 227 cross 227 cross 3 input image, or a bike is present in the input image, like that. Each of these 1,000 neurons represent actually 1,000 different object names of the data set. So this neural network was trained for maybe for 2 weeks to actually create this AlexNet. And we found out the weight filters, that is this 11 cross 11 filters, or these 5 cross 5 kernel filters in this layer. The weights for which the error is minimized is for weight matrices for which error is minimized is found in the case of a convolutional neural network. And that will be used during the testing phase. So in the testing phase, we will input a car image. After parallel convolution and max pooling operations, so you will get a probability of car neuron was 95, and other neuron struck will be 0.25, 25 percentage. Airplane probability will be 5 percentage. Ship probability will be 2 percentage. Horse race probability will be 0.5 percentage, something like that. Each of the 1,000 neurons will output. So the output uh, maximum output uh, maximum output will be car percentage is car because car is present in this input image. So by the probability value, we identify whether an object is present in the neural network or not. So now I am going back to the demo of one such neural network that can be used for X-ray classification. I'll go to the Colab. So So there is a library called Torch Vision, which has pre-trained models of uh, X-ray. So that's why I'm showing this. So you can install this library Torch by pip install Torch X-ray Vision. Uh, so once you have installed this library, you can import models from Torch X-ray Vision, which is the pre-trained models, and also I can import X-ray images. So I can in fact import by using Google Colab import files. I can actually import files from my uh, desktop itself. So there is choose file option, and from my download, maybe recent. So I'm now uploading this file, just plotting that X-ray image. I am performing normalization. So normalization, you know, right? Each pixel I will divide by uh, 255 to make it between 0 to 1. Then I will apply transformations like resizing to 224 cross 224, or then I'll load my weight metrics. So here I am loading a more artificial, like AlexNet, I am loading a neural network called DenseNet 121 with the 121 layers. And I have loaded the weights architecture of the neural network as well as the weights of the neural network, which will give me maximum accuracy during the training process. And when I apply my input image, it is telling that this is analytics with a 20 percentage probability, consolidation with 34 percentage probability, infiltration with 51 percentage probability, like that. So if I put a threshold of above 50, when all the diseases names like infiltration, emphysema, fibrosis, which I can use display to my user, as these are the diseases that are present in this input image. So that's a classification problem where you can use the model. So here I have not shown you the training process because of the lack of the time. But in the training process, you will give maybe 1020 or 1 lakh plus images of, and find out the weights for which the error is minimum for all the 14 classes. And for testing phase, so not only that it is used for uh, classification problem, we can also use for these neural network for segmentation problems as well. And one such example where X-ray torch vision is used for segmentation problem is here. Uh, so again, I can import the file from I'm uploading my input file, and again I'm loading my model for PSPNet, which is a model which is used for segmentation of body parts from chest X-ray images. Uh, so segmentation means I can extract heart region or lungs region associated with the chest X-ray image. Uh, and I am downloading the weights of this PSPNet architecture for which error was minimum, and so which is called as pre-trained weights. And I'm loading the model and I am supplying this input image G9210228, and then I will run prediction of. I will first normalize the image, resize to 512 because this model accepts 512 cross 512 images, and do the prediction. So the prediction output will be X-ray images with heat maps. So basically, the heat map shows left clavicle, right clavicle, left scapula, right scapula, left lung, right lung, etc. And if so, these heat maps are actually detecting each region of the X-ray. So like left lung, right lung, pulmonaris, heart, aorta, mediastinum, spine. So this can be used to effectively predict the different diseases and disease affected regions in or AI by the AI engine. So with this, I think I will conclude my presentation. So in my today's presentation, I have actually briefly covered uh, what are the kinds of chest X-ray, what are the medical applications of medical imaging, what are the uh, how image looks like in for a computer, and how X-ray image processing can be done, what kind of data sets are available for that, how to train an data set using artificial neural network or convolutional neural network, uh, and how to do predictions using a pre-trained model, and how to visualize the 3D images using DICOM and image IO libraries. So hope my presentation was useful for you. I expect you my small time that I have spent is will be helpful for your future endeavors. Wish you all the best. If there are any questions, I can take it. One or two questions. Uh, if there are no questions, I will disconnect. Thank you. Yeah, over to you, ma'am.
Thank you, sir. Participants, if you have any queries, you can post in the chat box now.
Anything? Any questions?
No questions, it seems.
Yeah, thank you, ma'am. Then I'll disconnect. Thank you for the
Thank you,
opportunity.
sir. Thank you for your informative session. We appreciate your valuable contribution for our FDP. Thank you so much, sir.
Okay.
Now let's move on to the next session of our FDP. We are delighted to welcome Dr. Hemalata Kanniyappan, an accomplished academic and researcher in the fields of biomaterials, tissue engineering, and biosensor technology. She completed her PhD at IIT Madras, where her research focused on developing nanocomposite bioactive scaffolds for bone repair and generation. Dr. Hemalata has also carried out significant postdoctoral research in the United States, contributing to advanced work in biosensors for early cancer detection, implant corrosion, and toxicity studies, microfluidics, and 3D printed regenerative constructs in collaboration with leading medical institutions such as the UIC College of Medicine. She's currently working as a lecturer at the University of Massachusetts, where she contributes to teaching, student mentoring, and ongoing biomedical research. Her research comprises of numerous publications and patented innovations to her credit. She has mentored undergraduate, graduate, and PhD scholars and is deeply committed to translating scientific advancements into real world medical applications. We welcome you, ma'am. Over to you now, ma'am.
Thank you, Dr. Jennifer, for your warm welcome. It soothes me a lot. Let me share my screen. Is my screen visible?
Yes, ma'am.
Yeah, thank you. Firstly, let me thank each and everyone and Dr. Jennifer and Dr. Anand for giving me this wonderful opportunity to talk to you all. Being the other part of the world, it always feels like a home to talk to our people. Thank you for this great opportunity to share some of my work, which I did in my postdoctoral tenure in US. Um, One stream of my work was the development of electrochemical biosensors for early cancer prediction, where I incorporated some of AI tools, machine learning algorithms. So I thought that would be a right topic to discuss. Yes. Today, the topic of my talk will be AI-based early cancer prediction using proteomic biomarkers. The flow of my talk will be like first I'll introduce you all about the cancer and the like the diseases or the disadvantages or the limitations for the current diagnostic methods and what are the ways to diagnose cancer and what are its symptoms, where we are falling apart in not significantly diagnosing the cancers, and then followed by what are the efficient method to predict the cancer at its early stage, mainly to improve patient survival rate, and then followed by the incorporation of machine learning. So I have divided my talk into three main streams. The first will be the cancer, introduction of cancer, what exactly it is. I know it is like too much of biomed, and moreover, the topic of this Atal FDP is AI in medical imaging. However, my topic is mainly based on AI in medical diagnostics. It is pretty deviated from the real topic, but I feel it is like much needed in current scenario. Yeah, so this is how the flow of my talk goes. Yes. Um, yeah. To start with, we all know cancer is a deadliest disease or disorder, right? But we actually do not know how exactly it is deadly. And globally, the number of new cancer cases are projected to rise approximately from 20 million in 2022 to 35 million. Can you imagine like almost 15 million increase by 2050, with death increase from 9.7 million to 18.5 million. Okay. And from this number, you can imagine how deadly it is spreading in nowadays, in current scenario. So what is cancer? So cancer is nothing but a disease, or you can also call it as a disorder of like aberrant growth of cells that occurs when the cells in the body grow and divide uncontrollably. As you see in the image, where you can see I have given the differentiation of the normal cells and the cancerous cells, normal cells and the cancerous cells, you can see the clear difference between the structural or the morphological characteristics of the normal cell and the cancerous cell. From this image itself, you can clearly say that there is something wrong with the cellular functions, right? Only the cell, if it is in a proper way or in a proper structure, it performs its duty. whatever it is assigned to. If it is not in a proper shape or in a structure, the entire function of the cell will be disturbed. Eventually, it leads to a lot of mutations and whatnot, lot of disorders. Okay. So these abnormal cells can form a mass of tissue called a tumor. Okay. And it can be due to genetic variations, mutations, environmental exposures like smoking, radiation, pollution. Even passive smokers can also get affected by cancer. If I say passive smokers, it's not like the one who's actively smoking, the one who is sitting next to him or her. Okay, even they are prone to get cancer. And infections like hepatitis B and several other infections. Even I worked on a project where a bacterial infection, oral bacterial infection, can lead to a oral cancer, which is like it starts from a periodontitis kind of gum disease, and eventually it ended up in oral cancer. So anything before it goes to a bigger stage, from the smaller point of view, it starts from an infection. And lifestyle factors like diet, physical activity, too much of salt, like fat consumption, all these factors lead to a deadly disease or disorder called cancer. Yeah. So this is again an interesting thing. There are more than 100 different types of cancer. So as even I didn't know that before I study a lot about of this cancer research. Before that, I knew like there is breast cancer or pancreatic cancer, because when I was working in the biomaterials, we aimed, our supervisor was aimed on working on pancreatic cancer. So we thought, okay, it's mainly on like superficial organs, which is more important. Only we knew that, right? But there are 100 different types of cancers which are classified based on the type of cells that become cancerous and where it originates. Some common types, as I mentioned before, lung cancer, breast cancer, prostate cancer, colon cancer, and skin cancer. Yeah. So this slide is mainly represents the statistics of cancer in worldwide and most focused on United States, as I stay here now and do a lot of research. So as you see, in 2025, the estimated of like 618,000 people will die of cancer in United States. Lung cancer and bronchus cancer. Bronchus is like kind of an air passage to the lungs. So that is like responsible for most deaths. So lung cancer is the #1 deadliest cancer, and also followed by colorectal cancer, and which is the second most common cause of cancer death, and followed by pancreatic cancer is the third deadliest cancer, causing around 52,000 deaths. So I want to state a fact that when I started working on this pancreatic cancer, which is like 2 years before, it was the fifth most or sixth most deadliest cancer. Imagine in a period of 12 months, it has become the third deadliest cancer. Then you can realize that how fastly it's spreading. And the pancreatic cancer is one of the deadliest one where there is no treatment at all if it is detected at a later stages. However, the other type of cancers, there is some kind of treatment or replacement. However, for a pancreas, there is no replacement at all. If a patient is diagnosed with a pancreatic cancer in an advanced stage, it's so difficult to save that patient, and in a period of 6 to 8 months, the patient may die. And imagine like how ruthless it is, right? So, as a researchers, what we need to think, the thing is there is no treatment or there is no replacement, which is like we cannot say there is no, right? So there is solution for each and everything. However, the intensity of like the solution, whether it can be easily targetable or no. So for what we can do, yes, at least we can detect or diagnose this cancer at an early stage so that there is a chance of saving that particular patient, right? So it has to hit our brain. Yes, there is something we can do. So, and this statistics, you can see a different type of cancers like breast cancer, prostate cancer, lung and bronchus cancer. And for female, breast cancer is the number one cancer which is commonly occurred in women in all over the world. Skin cancer, bladder, like kidney. So what not? It is like there are 100 different types of cancers. And the next slide will be the ranking of cancer based on its incidence or mortality or its survival rate. Yeah. So as I mentioned previously, lung cancer is the number one cancer, which is the deadliest cancer worldwide, globally based on its occurrence. So globally, lung cancer is the most frequently diagnosed cancer worldwide, followed by breast, colorectal, prostate, and stomach cancers based on 2022 data. In the United States, the most common cancers are like projected to be breast, prostate, and lung, followed by colon and rectum. However, the second ranking based on the death. So globally, lung cancer again is the leading cause of cancer death, followed by colorectal, liver, stomach, and breast cancers. In States, in US, lung cancer is the leading cause of cancer death for both men and women. And the third ranking is based on survival rate. The lowest 5-year survival rate, as I mentioned before, pancreatic cancer. Pancreatic cancer has the one of the lowest survival rates, with only about 12.8% of patients surviving for 5 years after diagnosis. Other cancers with poor survival rates include liver and brain cancer. And highest 5-year survival rate, like the skin cancer or testicular cancer, may have high survival rates, while prostate cancer are also have high survival rate of 88%. Okay, so this slide mainly explains you about the cancer of its ranking. So what are the symptoms? Say, for example, I'm like talking about lung cancer is the number one, the leading cause for death globally. So what are its symptoms? Just a cough that persists or with blood, wheezing, chest pain, fatigue, shortness of breath, unexplained weight loss. So we always recommend here in US above 40, a regular body checkup is compulsory. It's like you should do a regular body checkup, because given the facts of these symptoms, do you really think, do you expect that, oh, I got a cancer? No, right? Wheezing is just like a normal symptom like other infections. Chest pain. Chest pain, yeah. If you have a chest pain, it's kind of a severe condition or it's kind of an alarm. You need to go to your physician immediately and do your full body check. And then breast cancer. So women play a very important role in all the fields. So saving our women should be the first and foremost thing. So explain to your family, to your mom, sister, wife, who not. Like, you need to take care of their health. Okay. So lump in the breast or armpit, so many things. Like, as I mentioned, what are the symptoms, early symptoms like early breast cancer, breast pain, redness or swelling of the breast, changes in breast shape or size, so skin texture of the breast, so inverted nipple or nipple discharge. So all those are breast cancer symptoms. So I feel that we need to come out of that conservative thing, and we need to focus on the development of our nation and development of the human well-being. Okay. And as I mentioned, the deadliest cancer, one of the deadliest cancer with lowest survival rate is pancreatic cancer. So I'll tell you this pancreatic cancer symptoms are so vague, and there is no way that you say that I have a pancreatic cancer. No. It's so difficult to diagnose, because if you see the symptoms, pale and greasy stools, nobody is going to check our stool, right? Abdominal pain, jaundice, new onset of diabetes, change in bowel habit, indigestion, nausea and vomiting, weight loss, shoulder pain. All these are symptoms of pancreatic cancer. So with these symptoms, you could see there is no like alarming thing. Say that, hey, you have a cancer. No, right? So all these are normal symptoms, which is like similar to other infections or disorders, which we won't take care of. So that's the reason now that's the reason this cancer deaths are increasing rapidly. So yeah. So this slide, once there is a formation of tumor, the tumor, as I said, is a massive structure, the mass of the cancerous cells. The cancerous cells are the abnormal cells, which grow and divide uncontrollably. So this, from one side, it transfers to the other side of the body, right? So that is the process called as metastasis. Usually, if there is some bone infection, it metastasizes to breast. It leads to breast cancer. So whatever your body, inside of your body, it's all interconnected, right? So if there is some infection in some part of the body or some major organ, definitely it might lead or transport to other organs. So one of my project, I was working in the hip implant toxicity evaluation, where the hip implant is the total hip replacement, where they use the metallic implants, right? Over the years, the leachate of these metal particles, which are in ppb concentration, parts per billion concentration, transport to other organs and leads to the systemic toxicity of those organs. Eventually, it lead to failure of those organs, liver, kidney, so many. So that even that small metal particles are causing this type of infection. And imagine the uncontrollable cells transporting to other parts of the body. Imagine how bad it will create your organ function or the structural or the characteristics of that organ, right? So as I mentioned, metastasis is nothing but refers to the spread of cancer cells from originally primary site to other parts of the body. And it's a serious complication of cancer that can significantly affect a patient prognosis and quality of life. Prognosis is nothing but the diagnosis. So there are different types of metastasis: lymphatic metastasis, hematogenous, and transplant. Lymphatic is through the blood system or through the lymphatic system, and hematogenous is nothing but through the bloodstream. Transplant is through the organ transplant. So it starts with infection and eventually the cell will transform into a cancer cell. So this is about metastasis. Yeah. So what are the current diagnosis methods for this cancer prediction or the cancer detection? So cancer is diagnosed through a combination of methods, including medical history, review, physical exams, blood, urine test, and imaging, like the scans like CT, MRI, or X-ray. Like our previous speaker, he mentioned about a lot of X-ray thing. And so all these, the cancer can be diagnosed with the combination of these methods and also biopsy, right? So where usually they say that biopsy, like where they remove a tissue or cell sample and then send it to a pathologist, and then they will diagnose it step by step and they will give you a result. So biopsy, and again, it's an invasive method. So, and then they do cancer blood test. So what are the type of blood tests they do? With a different blood count level, tumor marker blood test, blood protein test, CTC, Gallery, proteomics based plasma test. So this is for mainly for lung cancer in general. And say for example, breast cancer. First they do breast exam, mammogram, ultrasound, MRI, CT mammography, biopsy. And for lung cancer, lung function test, bronchoscopy, CT guided biopsy, CT scan, MRI, PET. So, yeah, I have one more thing. Yes, pancreatic cancer is diagnosed medical history, physical exam, blood test, endoscopy, and CT scan. Similarly, so different cancers can be diagnosed with different ways or the combination of conventional methods, right? So, can you imagine what kind of limitations these conventional methods can pose? Hmm? Can you imagine like what kind of limitations all these current conventional methods? Can anyone post in the chat box like just name a few of limitations? What do you think? This current convention. Early detection is not possible. Excellent. What else? See, play around with the methods, whatever I shared it now. Sorry. Biopsy, interobservability, yes. False positive results, false negative results, excellent. What else? Don't you think less accuracy? Yes, good. Don't you think all these diagnostic methods are too pricey? And also, don't you think it is like it takes a lot of time? By the time they detect or diagnose the cancer, yes, the patient is like at a huge risk, right? Yeah, non-curable at aggressive stage. Exactly. Yeah, yes. You guys got it? Yeah. Limitations of current cancer methods include inaccuracy, risk of false positive or negatives, and invasiveness, right? Invasiveness, like patients suffer a lot. Biopsy is not that easy. We just say for by words or in slides, I just put a line saying that a small mass of tissue is collected. No, it's an invasive procedure, correct? It leads a lot of pain to patient and also too pricey, and this lead to unnecessary procedures and anxiety, delayed treatment, cost, and the healthcare system with advanced imaging techniques like MRI, PET, which are expensive and have many limitations, right? And also it can lead to inaccuracy and false results, false positive results, where the screening test can show a positive result when no cancer is present, right? Leading to an anxiety, the need for invasive or costly follow-up tests. There are so many cases which suffered a lot because of false positive result. Imagine if there is no cancer to a patient, however, the doctor come and say, hey, you have a cancer. That's it. The entire planning office system would be demolished, right? And then false negative, where cancer can be missed by traditional screening tests, resulting in a delayed diagnosis and treatment, which can affect the efficacy of the treatment, right? And limited specificity. And this is one of the most important limitation, specific test, because most of the cancer diagnosis method lacks specificity. I would have gone to check for one particular disease for one particular organ. Doctor come and says, hey, you are not affected by that organ. However, you are affected by the different organ. What's the point, right? When I go with the pain of my stomach, they say that no, you don't have a stomach pain. Instead, you have a brain cancer. There is no point, right? So there is a lot of controversies and happening in terms of this inaccuracy and false results with the conventional cancer diagnosis, mainly based on its specificity. And yeah, as I mentioned, invasiveness, right? Invasiveness, most of the cancer method are invasive, like the tissue biopsies, certain screening methods, which can lead to complications like infection and injury. Exactly. When they are trying to do some biopsy, the surrounding area cells will also be affected, right? So if there is some infection, it's not that easy to, I don't know how many of you work with a cell culture lab. So when you work with a cell culture lab, first and foremost thing, we always focus to avoid contamination. Imagine just 25 T25 flask, 25 millimeter square, centimeter square flask. We are focusing that much, then imagine our entire body, how careful we have to be, right? So if we are trying to biopsy or remove a tissue sample, obviously the surrounding cells will also get affected, get infected. So then doctor will start with antibiotics. Again, that is a different story. So all this are too risky. So invasiveness and risk, high cost, expensive technology, advanced imaging techniques like MRI, PET scans are expensive and not always cost effective for routine screening. Downstream cost, patient financial burden. Not everyone are affordable to give that much money for the treatment or for the diagnosis, right? And other limitation, as you all mentioned, late stage diagnosis, evading detection, lack of evidence, time consuming, limited availability. So with all these current limitations, it is giving us a way, or it is making us to think, hey, you need to develop some method that can overcome all these limitations and can provide a better strategy to diagnose or predict the cancer at its early stage, or for the recurrence, or for the treatment, right? Yes. So to that end, nowadays in last few years, people or the researchers are focusing more on proteomic biomarkers for cancer prediction using different sensor methods. So with the given introduction about cancers and the cancer symptoms or the severity of the cancers, now we are slowly moving on to the, like we are trying to narrow it down. So now we are slowly going to a proteomic cancer biomarkers. So as I mentioned before, one of the main limitation is invasiveness, right? So to avoid that, why don't we think the protein cancer biomarkers present in different biological fluids? In our body, there are different biological fluids, right? Like sweat, urine, saliva, serum, so many biological fluids. So if I ask a patient, instead of giving you a tissue sample, just give your urine so that I will diagnose whether you have particular disease or not. The patient will be very happy, right? So even rather inside doing the tissue biopsy, just collecting blood, that is also not that much invasive. It is still invasive procedure, but not that much or risk associated compared to the biopsy procedure. So in with that idea or whatever, so we try to focus on proteomic cancer biomarkers. So they are nothing but the proteins that can help detect, diagnose, or predict the cancer the prognosis and treatment. Okay. So these biomarkers present various bodily fluids like blood, tissue, or tumor tissue, and the presence and the levels indicate the presence of cancer or characteristics. So to be more clear, so there are some proteins associated with each and every type of cell and its function, right? If a cell is not in its good shape or not in its proper function, eventually the proteins will also be affected, correct? So either the levels, the secretion of the proteins, either it can increase or it can decrease, but not definitely at the proper level, correct? So that's the main goal we wanted to select, especially when there is a tumor tissue present or the cancerous tissue present. These protein biomarkers will be in elevated levels abnormally. So the level of this protein present in that particular cancer will be higher in level. So that is one point of like one advantage of using protein biomarkers. And the second one is the certain cancerous cells will secrete one particular type of proteins. So which is like, you can say, hey, Hema is performing, Hema is teaching. That is the main role of Hema. However, if somebody comes and say that, hey, I saw Hema and dancing school. During official hours, no, that's completely different. Then something wrong in me so that I'm doing the other job. Similarly, a cancer cell can secrete a different type of proteins that is also associated for the cancer, and that also we can use it for the diagnosis of that particular cancer. Example include fibrinogen for pancreatic cancer, certain proteins. Yeah. So this patient-derived derivatives and omic analysis. This proteomics helped a lot to identify that particular proteins, analyzing the large set of data, utilizing innovative technologies, and finally to the clinical research. Yeah. So types and applications of proteomic biomarkers. So early detection, as I mentioned, it is widely used for early detection. It's an amazing idea to use this protein biomarkers for the detection of cancer. I would say, I personally feel. And diagnosis, prognosis, some biomarkers provide information about how aggressive a cancer is likely to be and what the likely of the outcome. As I mentioned, the funny example before, and treatment response. Even after recurrence of the cancer, once it is removed, there is a chance of getting back, right? So there is chance of recurrence. So during that time also we can use this proteomic biomarkers. However, what are its challenges and future direction? See, I bet that you all know about the research, right? How it works. We think that, oh, hey, I found this solution. No, there will be something better than that. That's the reason we say that research, right? Always we are doing researching of what is already been given. So even though I boast a lot about this protein biomarkers, it has its own limitations and challenges. So identifying a potential biomarker is the first step, challenge, and rigorous validation to ensure it is a reliable biomarker. Again, so we cannot take risk with patient's life, right? So we have to be very sure to select that biomarker, and rigorous validation. We need to validate, yes, this biomarker is responsible for so and so cancer. And then integration, combining this proteomic data like genomics, and it's a very well good approach for understanding of cancer and robust biomarkers. And many proteomic analyses are complex and expensive. So the future goal is to develop simpler, faster, and cheaper assays for widespread of clinical use. So as I mentioned, proteomic biomarkers, protein biomarkers are nothing but the some proteins which are responsible for that type of markers, which in turn where the levels of that particular proteins are elevated in different biological fluids if there is a chance of that particular cancer. For example, breast cancer. So if there is breast cancer, you can say these proteins like MMP9, ECM, BCA225, ALP, there is one more specific to breast cancer is aptaglobin. So they do test. Even nowadays, the conventional method, the blood test, they use proteomic biomarkers, as I mentioned in before in diagnosis. And then prostate cancer, all this, and pancreatic cancer, CA99, CA24, all these are proteins or enzymes which are present in an abnormal levels when there is a chances for the cancer, right? Lung cancer, liver cancer. So I have collected this. This is basically I did for the, when I tried to apply for a grant, I tried to create this image, and I took almost 30 days to create this image because it needs thorough validation and comprehensive understanding, and you need to read a lot of research articles and create an overview of protein biomarkers in different cancers. And we even published proteomic-based electrochemical cancer, non-invasive cancer for early breast cancer prediction. And in this work, we just use only one protein biomarker, which is ECM1. Yeah. So here in today's talk, I'm not going to talk about all the cancers. I'm just going to give a example. So I just created, I just explained you a one condition where we understood from the scratch like what exactly it is and what can be done and what can be done to overcome the conventional method limitations. So now we came to know that protein biomarkers can be used because these protein biomarkers, as I mentioned here, it is present in different biological fluids, saliva, urine, blood, or serum. When you take breast cancer, all these proteins are present in urine. So it's so easy for a patient to give a urine sample rather than giving a tissue sample, right? And even saliva. So saliva, I'm telling saliva, there is a hub of protein samples and where you can detect a lot of disorders or the diseases, right? And also we know it has like more than 600 different bacterial microbiome. So yeah, saliva is like a very good sample for disease detection if we understood it very clearly and if we thoroughly read about it. And blood and serum, as usual, it's like the direct, there is no chance kind of false positive or false negative. It gives a very accurate results comparatively with urine and saliva. As I mentioned, like urine and saliva, it has a lot of other combination of biological molecules. So kind of false positive or false negative will be there, but that can be ruled out with a combination of different biomarkers. Right. So in this work, we just used only one biomarker. With only one biomarker, I cannot say, hey, you have a cancer, right? So I might create some kind of anxiety and also I might be wrong. So to overcome that, we need to use combination of different biomarkers. And then breast cancer, yeah, we worked on the breast cancer. So I'll just explain about briefly about the breast cancer. Breast cancer is the second most cancer in the US for especially affecting women, and more than 2.3 million cases and 685,000 deaths are reported annually. Different stages of breast cancer are as follows. Stage 0, where the cells are present, like aberrant cells are present, but they are not ready to spread. Okay. Stage 2, and also they are ready to, it formed a tumor, right? The first stage, there is no formation of tumor. Tumor, as I said, is the massive formation of abnormal cells. And then slowly, it's surrounding tissues. Stage 2 and 3, it starts to migrate, metastasize. And 4 is, it completely goes travel to the other organs of the body. So these are the different stages of a cancer. So for any cancer, there is different stage. Lung cancer, tissue, like pancreatic cancer, breast cancer, oral cancer. For any type of cancer, there is a stages. So if we detect or if we predict at the early stage, like stage 1 or stage 0, there is a chance to save that patient. Even stage 2 and 3, but with the rigorous treatment like chemotherapy and so many things. Okay. Yeah. So as I mentioned before, there are different biomarkers can be used like ECM1, MMP9, haptoglobin, BCA 225, ALP. Yeah. So first thing we need to know what are the normal levels or the different levels of these particular biomarkers in different stages of the cancer. So to start any research, so yeah, after selecting of this particular cancer I am going to work on, and after the selection of particular biomarkers, then I need to understand the levels of this biomarkers, right? So yeah, there is a level, for example, haptoglobin. So it is present in both serum and urine. So normally the level of haptoglobin present in serum is 25 into raised to 10 raised to 3. However, in urine, 5 into 10 raised to 3. Once this level slightly increases, there is a low risk, right? There is a stage associated with stage 1 or stage 0 or 2, stage 1 or 2. And if it exceeds even more 250, it is high risk. So we need to know these levels, this biomarker, and what are the levels of this biomarker at normal, low risk and high risk. Yeah. So to detect this breast cancer, currently they are using MRI and biopsy. As I mentioned before, these techniques are expensive and more painful. And also it can be more difficult to the, like it is usually diagnosed at the later stage of the cancer. And we are trying to create or develop an affordable, portable, non-invasive cancer diagnostic system. Okay. Yes, to that aim, we are focusing on the development of electrochemical biosensors. So far we have come across what are cancers, what are the severity, and what can be used to overcome the current limitation and bring a diagnostic method in an affordable way. So we are trying to use proteomic biomarkers. In which way, right? Using which technique we are going to use these proteomic biomarkers for the detection of cancer, right? So we are focusing on electrochemical biosensors. So as we know, sensor is nothing but a device that produces an output signal to detect any kind of changes in the physical phenomena. Right? We have pH sensor, you all know about pH sensor, temperature sensor, humidity sensor, everything, just to give you an output signal in the detection of the physical phenomenon, right? And what are biosensors? So biosensor is an analytical device used for the detection of chemical substance or any substance that combines with a biological component with a physiochemical detector. Okay, so what are the elements? Bioreceptor. So first is the bioreceptor. So bioreceptor, where there is the biological event occurring in that bioreceptor. So nothing but the interaction of biological molecules present on the receptor. And this interaction between these biological molecules will create some kind of biological signal, right? And there is enzyme lock and key model. So simple one. When there is a lock inserted into, when a key inserted to a lock, it locks. Either it locks or it opens. It's kind of an output, right? So there is some kind of biological signal. So that biological signal will be transduced. These transducers will convert those biological signals into electrochemical signals or the biochemical signals and process it to the signal processor. So that biological recognition or the biological event will be recognized by these transducers and convert them into a readable outputs. That readable outputs can be of any type. So since we focus on electrochemical, that readable output will be in terms of electrochemical assays and the results, and that will be processed with the signal processors. So any bio sensor has 3 elements: bioreceptor, transducer, and signal processor. So we usually, as I mentioned, like as I told, like electrochemical measurement sensor, we used this type of chip or the electrode. You can see the working electrode. The working electrode is the gold electrode. We used gold electrode, and some methods we even use the advanced carbon-based materials for better electrical signals. And then we use the reference electrode AgCl, counter electrode is platinum. So what we do do a series of incubating steps or the functionalization onto this gold electrode and make this biological event occur. So this is the bioreceptor. This gold electrode is the bioreceptor, and we do the series of interactions. Okay. So yeah, as I mentioned, this converts the information associated with electrochemical reactions into applicable qualitative and quantitative signals. The bioreceptor, whatever the biological interaction occurs, the transducer, which is nothing but the electrochemical passing of different electrons, converts them into an converts the electrochemical reactions into an applicable quantitative or qualitative signal. Okay. So nothing but the reaction between an electrode and analyte. So this analyte can be anything, right? So even in our body, so usually, I don't know how many of you use this Apple smartwatch, right? Nowadays, you use a lot of smart things there with the advancements in technology. So they say, right, with your hand, they measure a different heartbeat. So like BP, and what type of analyte do you think it is present? Basically, whatever the smartwatch is like electrodes. Like what type of analyte do you think it's present? You are wearing a smartwatch, right? So what do you think analytes can be used? Don't you think sweat can be used, right? Yeah. So I just saw, ma'am, is there any protein biomarker for blood cancer? Yeah, there are a lot of blood cancer protein biomarkers. For example, I think CD22 for B cell lymphoma, or 25 leukemias, blood cancer. Yes, there are a lot of biomarkers for blood cancer as well. So yeah, so sweat can be used as an analyte. And what for the lab we did with the PBS or the saliva or the urine, all those samples can be used as an analyte, right? And different types of electrochemical biosensor. It can be amperometric biosensor, where it measures the current when produced when a reaction occurs at an electrode surface. And potentiometric biosensor measure the electric potential or the voltage of a solution. Conductometric biosensor measures changes in electrical conductivity. When the target substance interacts with the sensor, it changes the conductivity of the solution. Yeah. So as I mentioned before, this is the working principle. First, the biocompatible layer. This layer where all the biological events occur. So what do? So on this top of the electrode, you functionalize those electrode with particular antibody, and then the protein, we code that particular protein in different concentration, right? Proteins and antibody, they merge together, they couple together and create a biological interaction, right? So, and then the transducer can be electrical, optical, or physical, and then it amplifies signal and then data process. So this is the main working principle. And what are the advantages? High sensitivity and specificity. Analytes or the proteins, the sample. So the sweat, there is some excretion of proteins. Saliva, there is protein, and blood, there is protein. So here we focus on antigens as the analytes. Okay. Advantages of biosensor: it is highly selective and specific, less solvents and organic reagents, disposable and fast. It detects very fastly, user-friendly, efficient and cost-effective, transportable, and stability. You can imagine, right? It's just a chip, a normal chip. So what we thought is it should be similar to kind of a pregnancy kit, right? That's what pregnancy biosensor. Pregnancy kit is also kind of a microfluidic chip where you code this HCG, hormone, and check for the positive or negativity of the pregnancy hormones, right? So we wanted to develop that type of a point of care device for cancer diagnostics. Yeah. So yes, as I mentioned, working electrode, we have the sample biomarkers, and then this sample biomarkers can be attached to a receptor. The sample biomarkers are nothing but the ligand, and this one is the receptor. To be more clear or in a easy way to understand, just imagine or just think lock and key model. Okay, so key is your sample and the lock is the receptor. So the proper lock and key. So one lock will have only one particular key, right? So when that particular key go and fix it to the lock, it fixed firmly. Otherwise, there is no point. So yeah, so the sample and the receptor, it can be enzyme, protein, nucleic acid, and antibody. Once it is done, it passes to the transducer. Transducer, as I mentioned before, it can be electrochemical transducer. That's mainly of shuttling of electrons. And light transducer, which is like optical. I even worked with the molecular beacons, which is again development of optical biosensors for detection of bacteria. That's again a different story. Again, it is similar to electrochemical biosensors using molecular beacons. That is optical biosensor, not electrochemical. And then gold piezoelectric transducer. So using all these different types, it produces the signal. So the output parameters will be, as I mentioned, since we are focused on the electrochemical, EIS, Bode electrochemical impedance spectroscopy, it's nothing but the charge transfer resistance between the electrode and the analyte. And then cyclic voltammetry, I'm sure that most of you guys know about this cyclic voltammetry, CV, oxidation and reduction reactions. And then so many, imagine, so we are just doing a biological assay and trying to get an electrochemical data for that particular biological assay. How cool it is, right? And this is where we need to appreciate the development of or the advancement of technologies. And slowly we are going to incorporate machine learning. So this is kind of an interdisciplinary research. So biologist, and then we need a material science or the chemist for the electrochemistry, and then we need a computer science people for the machine learning to develop one particular device, right? To improve our human lives. So this is the working procedure. I just rush into this because I'll just explain what we did exactly. We just clean the sensor and incubate with the specific chemical cross-linking agent, so that because it's a gold surface, right? And we need something to attach onto the gold and the antibody, because that's a biological molecule. And this one is a gold and then metal. So we need to attach this gold to the biological molecule. We use some kind of cross-linking agent and the antibody is fixed onto the surface of the electrode. And then series of different steps, we are planning to add this particular protein. So we selected certain proteins. So in this, I'm just going to give you an example of a protein which is responsible for breast cancer. And then we added that particular protein at different concentration. So we wanted to check the concentration dependent electrochemical sensor, right? Because at higher level, there is a chances of higher risk of cancer. At the lower level, it's a low risk, and normal. And then we did different concentration and tried to collect different electrochemical results like EIS, CV, open circuit potential, and whatnot. There are even more advanced ones, square wave voltammetry, differential pulse voltammetry. So actually that's a different lecture. Yeah. So what do we get from electrochemical biosensors after all this interaction, transducing readable parameters, open circuit potential, EIS, electrochemical impedance spectroscopy, which is nothing but this charge transfer resistant and the diffusion resistance. So where you can see this semicircle followed by the straight line. So this is kind of Nyquist plot where it explains the charge transfer resistance of the analyte present onto the electrode surface. Say for example, if there is something present onto the surface of the antibody, so I am attaching the protein, right? Either the reaction or the interaction, it will increase the response or decrease the response according to the species or the biological molecules present on the surface, right? So this charge transfer resistance increase or decrease mainly based on the different species present, and also we can get the double layer capacitance. In this work, we mostly work on the double layer capacitance. However, in bacterial detection, we did this charge transfer resistance. So check. If you see this slide, you can see for EIS, I'm getting Bode plot, Nyquist plot, change in impedance. And then the model I use is from the model, I am getting resistance, polarization resistance, constant phase element, solution resistance, and CV, I'm getting area. So you can imagine how many parameters I am getting just for one particular protein. And I am going to do that particular protein in triplicates, right? So I'm just using one protein, triplicates, I'm getting almost more than 10. I would say more than 10 output parameters I receive from a single electrochemical study. So this is like how it exactly looks, Bode plot and Nyquist plot for the concentration dependent study is just an example for you to see with the concentration, the changes in the response curve. And change in impedance, change in capacitance, cyclic voltammetry area. So you can clearly see that if there is change in concentration, the change in response is very evident, right? So, and each concentration we did in triplicates. So one protein triplicates, and each concentration in triplicates, we get tons and tons of data, right? So though we do this biosensor, electrochemical biosensor for cancer prediction, it has its own challenges. So we need multiple biomarkers to rule out the false positive or false negative thing, and tackling the variability in biofluids, especially urine, right? And then imagine, as I mentioned before, it has a large data sets and accessibility for large populations, so many, right? So, yeah. So here our main hero comes into play. Like you all, we need the help of machine learning expert to help us with this analysis. We can't, it's like, I don't know, humanly it's impossible to analyze, how many origin graphs I will sit and plot, or even though after doing all this analysis and everything, there is a tons and tons of data which takes a lot of time to analyze or thing, right? So that won't be efficient. That's not an efficient way of doing research. And we need to utilize the technological advancements to make a research more effective. Here our machine learning person comes, and yeah, what are the challenges and analyzing data, sensing data, machine learning is in focus and novel strategies. So what we did this machine learning and we called it as an intelligent biosensors. So for our study, it's just, we gave a name for that particular biosensor. We incorporated some machine learning algorithms, and then we named it as intelligent biosensors. Yeah. So yes, all these talks, you've been listening artificial intelligence, machine learning, and there is no need for me to explain in detail, right? So as we all know, artificial intelligence is a broad concept of machine performing that particular task, while machine learning is a specific subset. We know, right? Artificial intelligence is the overall picture, and the specific subset is machine learning. Even more specific subset is deep learning. It's kind of the family generations, great grandfather, grandfather, and father. It's like big picture and the middle one and the smaller one. In simple terms, ML, machine learning is an algorithm, is AI, but not all AI is machine learning. That you all know, I guess. And you know, this machine learning or the artificial intelligence is project now everywhere is AI, machine learning. So it is projected to have a market size of 266 billion by 2027. So what exactly it does? Machine learning intelligent biosensor, direct and fast readout, improved reliability, improved accuracy, improved specificity, and ultra sensitivity, right? So the sensitivity and specificity are most important parameters in almost all the analysis for this cancer prediction. And there is one paper where they used SVM data to analyze EIS with accuracy of 98%. Yeah, so as I mentioned, what exactly this machine learning does in several ways, categorize the sensing signals in various categories algorithms. We have a lot of electrochemical signals. First, it has to categorize based on the particular analyte, which is the protein. And then anomaly detection, it has to detect what are the faults or like what are the things which affects, like when a biosensor used on site, they can significantly interfere with contamination, right? So this machine learning can check that signal and answer the question, does the signal look right? So see, anomaly detection for the cancer prediction and noise reduction. Noise is always included in sensing signals. That is there everywhere, almost all the characterization methods. So the signal from biosensors changes over seconds or minutes, while signal interference such as electrical noise can occur on the sub-second timeline. So it is also possible to train this ML model to differentiate the signal from the noise. We need only the proper signal, not the noise, right? And also object identification and pattern detection recognition by discovering latent object or the patterns using machine learning algorithms. Sensing data can be interpreted easily and effectively. Yeah. So nowadays, in machine learning, biosensor has been a wonderful tool for the detection, for using this, analyzing this large set of data. And also it can be classified in supervised learning and unsupervised learning. It's mainly based on the training of that particular model, whether you're going to train with the group of input data with target outputs or with the no given outputs are available. That is unsupervised learning and supervised learning. And again, one more thing, like whatever the machine learning or whatever the algorithm we write or like develop, it's mainly the based on the input, whatever we do, however we train the model, right? So different algorithms have been used for the biosensors. So I have created not created, I'm sorry. I have pulled out a table from a research article where they gave a very good comparison with of various AI algorithms that are used in biosensor application. As you see, the methods like SVM, neural network, like conventional, so many machine learning algorithms have been nearest neighbor model. So many machine learning model have been used, right? Yeah, you're right. So there are so many machine learning models, algorithms have been used for the application of biosensors. And they have given some drawbacks. Everything has its own drawbacks. Hmm? Yeah. So yeah, how do we train the model? I think by the explanation with the previous talks, you will be knowing that we are to train the model, which includes training set about 60%, validation about 20%, and test data about 20%. Like training data set is nothing but the exact meaningful information and the hyperparameters. And validation data, while tuning the hyperparameters, the other outer layer parameters, and the test data is employed to report the performance of the algorithm. Okay. Yeah, so I don't think so. I want to go into deep of all this, and this is the main like figure where you can see the raw data, data processing, and then you have to train the model and validate and testing, and you get this overfitting or underfitting. You can overcome this overfitting or underfitting by regularization intensity. So hyperparameter, work on the play around with the hyperparameters and the algorithm. And this guy is this predicted class where you can see the figure C, which gives the matrix. The result form is nothing but the confusion matrix, where the true positive, which is like truly associated with that, and false negative, where it differentiates the different classes. Say, for example, high risk, low risk, and normal. And with respect to different concentration, it clearly differentiate. And also the calculation of accuracy, precision, using all these formulas, you can predict the model accuracy. So in our work, we used SVM model, which is a supervised machine learning model used for classification, and it clearly distinguished cancer and non-cancer signals. And then yeah, how it works, we give some data input, electrical signals, impedance, and fluorescent intensity correspond to the presence or absence of biomarkers. And then the important feature or extracted from the biosensor data, like the current time or the frequency range. Like usually we give from 1 hertz to 1,000 kilohertz, and then finding hyperplane and two classes, 2D method, and maximizing the margin. So all this, how SVM works. So advantages of SVM, and I know that SVM is a basic model. So we just wanted to start with something basic and more easy to understand, and easily applicable to the cancer biomarkers. And then we started with SCM. And then neural network model is a machine learning model, is inspired by the human brain. It is desired, so it's kind of bit advanced model. So we wanted to select both the basic one and the advanced one. So we selected neural network and the cancer prediction biosensor uh, to identify whether simple or a sample is cancer positive or healthy, and again how it works. So this is the it's just about the basics of SVM and neural network model. Yeah. So for our experiment, what we did. So first we developed a Python model, automation model. First we ran EIS, CV, open EIS and CV files, data files, fit into an impedance model, select CPE. So first we run on Python and then automation model. We wrote a Python code and we ran an automation model, and then we we trained the model with different parameters. Like this is just an example, and you can see it is a small. You can think it's a small set. No, it definitely not like that. We had like almost the Excel sheet. We had more than 10 to 15 or 20 Excel sheets with different biomarkers and different triplicates and different parameters, and associated with normal, low, and high risk. So then we trained the model with training 80% and validation 20%, SVM and neural network model. Finally, we got this confusion matrix of accuracy 98% and 76% with the neural network model with a different thing. And this is just for the aptoglobin. However, we have 5 different biomarkers for urine sample for breast cancer prediction. And imagine this 5. So that's our next study, and we already almost completed that, and we are doing it for breast cancer, we are doing it for pancreatic cancer, we are doing it for oral cancer. So we are doing it for a different type of cancers using different biomarkers, using different using this electrochemical method. So our main goal is to like collect that sample, just the urine sample, and machine learning, use this chip and send it to the medical practitioner, and immediately he will give you an advice on what exactly to be done, follow up. So our main aim is to detect early detection. To summarize everything, we understood like what are cancer and what are the severity and what are the proteomic biomarkers, and how beautifully this machine learning is helping to analyze the large set of data and then give us the confusion matrix, and with just saying that low risk, high risk, and normal with an accuracy of good accuracy, I would say. But this is not exactly the data. I'm just giving you an like I would say it's a lab like unoptimized data. So we have very good, we have got very good accuracy because it is not yet published. So I don't want to give the exact results or the exact table. Yeah. So finally, this is kind of a futuristic view. I have pulled out this image from a article. I thought it is more relevant to the study which we are focusing on. Just it should be a point of care device, and it rule out the cost effectiveness and invasiveness, and so we don't have to worry. Just doing like a diabetes test at home, diabetic with using a diabetic kit. So just have to insert a blood or urine or saliva onto the chip, and it undergo or it process and it analyze. So this processor, and where we fed all these trained models into that, and it just gives you chemo 1, chemo 2, or chemo 3. So for us, we just have to give low risk, high risk, or normal. So this is our main thought to create this type of a thing. And you can also use optical biosensors to combine and create this type of a microfluidic device. Yeah. So this is how we did the research. Yeah. So yes, I have few questions. Cancer disease is a rare type, and do we have a sample size? How you get? I don't understand which cancer disease is a rare type, and we have sample size. How we get accuracy? Okay. So there is no small sample size. That's what I'm explaining. The electrochemical data sets, or like, yeah, source of data sets are the data sets where you are getting from the electrochemical data, change in impedance, delta C, or polarization resistance, or from the model. All this we use. And then it is not a small size, to be honest. It's a huge and large data sets. So if you have performed electrochemical analysis before, you would have known that it's a large data sets, because we want to do a rigorous validation. We cannot give any type of false positive or false negative results. That's the reason we are incorporating machine learning to analyze all those data sets. And then these are the few references. Thank you. Thank you. Thank you for inviting me to this talk. I hope you understood.
Thank you, ma'am. It was a great session. I think a few questions are being posted in the chat box, ma'am. Any suggestions on omics data, so multi-omics data set?
Multi-omics data set, again, it's mainly based on the proteomics, the protein data set. You need to train the model with the different proteins, and then, yeah, you can do that with omics data set.
Okay, ma'am. I hope the questions are over. Thank you, ma'am. We express our heartfelt thanks to you for sharing your deep expertise and your thought-provoking ideas during today's FDP session. Your presentation was very informative, and it has given our participants a clear understanding of the subject. We are grateful for your time and effort.
Thank you. Thank you so
ma'am.
much, Jennifer. Yeah.
Thank you, ma'am.
Have a wonderful night.
Good evening, ma'am.
Yeah.
Ma'am, I'm Kirtilata from Stanley Engineering College, ma'am. I have one question, ma'am. Here you are talking about different data sets, no, ma'am, regarding the breast cancer, if I wanted to highlight. Because in cancerous stage, we are having different stages, stage 1, stage 2. So how do we sense with real time? If I am using a real time sensors like bio sensors, what you are telling, and if I wanted to analyze the data, because these machine learnings will be working on a huge data sets. But if I wanted to work with the real time data, will it be possible for a researcher, a scholar, to get such a huge data where we can apply these machine learning algorithms and proceed further?
Yeah.
And
that's
find
an
out the
excellent
stage in which the patient is.
Yeah. That's an excellent question, Ms. Ketilata. So actually this stage, as I mentioned, different biomarkers, right?
Yes, ma'am.
So I have selected 5 biomarkers, correct? So ECM, ALP, MMP. So each biomarker associated with particular stage. So that's the reason it is giving low risk. The low risk might be between stage 1 or 2. So you can play around with the selection of biomarkers. Yeah. So in this ECM, MMP9 are associated with early biomarkers.
Okay, ma'am.
So when it is mainly associated between the stage 0 to 2 or 3, that is imposing low risk. So
Okay.
what we are suggesting, yeah.
Yes, ma'am. Proceed, ma'am.
Yeah. So what we are suggesting, like training the machine learning model is even at this particular lower concentration of this particular marker, give it as low risk. So we are training with different parameters for different biomarkers at different stages. Yes, you are absolutely right. Each stage has different levels of this protein expression. For example,
ma'am.
this aptaglobin and BCA225, it's like highly expressed. It is more specific to the breast cancer. They are not expressed in any type of other cancers. However, certain biomarkers can be expressed in other type of biocancers as well. So that will give you a kind of false positive. So to overcome that, we are using more specific breast cancer biomarkers. However, these other biomarkers can express in the lower levels at the early stages. Yeah.
Yeah, okay. But as a scholar, if I wanted to take a general data set which is available for to do research, will these biomarkers will be mentioned in the data set? It won't.
Yes. Yeah, they will be, but you need to do a lot of research. You need to read a lot of papers, go to cancer statistics or American Cancer Journals. Like they will mention this biomarkers. Yeah. If they are trying to file a patent, it won't be visible. Yeah.
Okay.
Yeah.
But
Thank
what
you.
general question we will be, as a scholar, we will be facing from the evaluators is like, if everything, if we are taking these signals directly from database available, we are not doing any pre-processing all these things because data is purely available with removing all the noise and all.
I would say, see, the functionalization of electrode, see, as in a research scholar point of view, the functionalization of electrode itself a different procedure, right?
Yes.
And that also you can show some kind of novelty. So not necessarily use that particular cross-linking to give some kind of signals. You can even use the different cross-linker to enhance the electrochemical signals. So you need to play around with the different selection of different molecules to enhance the electrochemical signals. Then you can create your own data set and create your own data model. Not necessarily that particular set. And that's the reason there are a lot of market products are available, right? Say for company A is also giving pregnancy test. What is the need for company B to give another pregnancy device?
Yes, yes, sir.
Yeah. So it
With the same biomarkers, can we be able to get the signals from brain also? EEG signals also can be extracted from these kind of biomarkers where the chemical component can
I
be.
think there are few biomarkers can work, but not all. But I think I have read some paper, there is some few biomarkers can work.
Okay.
Yeah. Eventually, the EEG signal will vary, right? The response of the signals will vary with the presence of different biomarkers, correct?
Okay. Ma'am, when we are evaluating the model performance, we are mainly concentrating on precision, recall, and F1 score and accuracy. These are the 4 main parameters where we concentrate in evaluating the model. Is there any other parameters that we can concentrate to evaluate our model?
To be very honest, we focus mainly on accuracy.
Okay.
So because that's how the market is working. If I give a model or give a device with 95% accuracy, my competitor just say 95.5% accuracy and claim his thing is working very well. So in market point of view, you need to focus more on accuracy. That's how I personally feel, in a more
Okay.
realistic way.
Okay. Thank you, ma'am. It was a
Yeah.
wonderful session.
Thank you. Thank you.
Thank you.
Hi, ma'am.
Hi.
Ma'am, I'm Harpreet. I'm working in a Jain University right now, and I have one question. I'm working on a Brett's data set for a brain tumor. So, we require a really big GPU. As you just mentioned, in the market right now, it's going on. Like if someone got a 99, that is, they get a better result, it means. But when we start working, actually, we don't have that type of tools like a software, because we require the big GPU if we don't have a workstation. So if we work on the model with a small data set, so it's very difficult to publish a paper in a good journal. Na? So can you just suggest anything regarding that, how we can? Because nowadays everyone is ni- no one like below 95. It is 95 to 99.8, even
I
99.8.
won't agree to that. 99.8 is like, I don't agree. No. See, ultimately, you're going to train the model, and whatever
I
I
see,
train.
ma'am. I experiment with so many models. It never reach like if we go for a dice score, everything, na, it never
Yeah,
reached to like 88. Going to 91, it is the breaking, it is not a continuous. But I don't know how they publish it is a 97, 98. And I am unable to understand. And they are in the big journals. And even I send an email to those people, like I try to implement this, and I never get a reply from anyone.
But Arprit, so that's how the scientific thing is working now. So especially if you are in a materialistic country kind of US, so you need to focus, you need to work hard, and I also have that type of doubt. I always tell my students, don't come with confusion matrix saying that 100% accurate, 99% accurate. No, there is nothing you can get for 100% or 99%, especially for biological samples. No, you can never ever get
Never,
that.
yeah, ma'am. It is
So,
definitely because and I feel like what is the purpose of the big journals to write the things now? So seriously, many time I started essay paper and like who will guide? And the person who is like the guide to us, they said, ma'am, we can't go for essay na, until like we need some sponsor person for publish the paper. That is a big thing. And the second one is the whoever is guiding us, they ask, oh, come with a better result. Only that's possible to publish in a good journal. Otherwise, it's very like at that time you feel like the good work is not a worth it.
true, true. I understood, but I would say don't lose hope. You are there. Already you are there. One thing I really like with you is you are asking it directly. So that's the way a researcher should be. So no matter whether right or wrong, question it. You are questioning it. That's a really a good thing. I appreciate it. But there is some reality check. There is some reality. Certain times you need to go with the flow. Just go with the flow. Try to do with the small data set. See, with now there is a lot of competition with machine learning, and they publish like anything just
They
because.
publish, yeah, that's a problem, ma'am. That's where I feel, and from the last 2 years, I don't want to publish anything. I like what's happening now.
Yeah,
Anyone
that's what
can
I
publish.
said. Don't lose hope. You need to work. So just get into the race. It's kind of an horse race. Research is not that thing that easy. We think that, oh, you are doing just research. No, no, no. It's an horse race. As long as you run, you go to a way where you want to reach. The moment you think or step back, that's it. There are tons and tons of horses behind you to run
Yes,
and pass,
yeah,
go
ma'am.
past you. So just focus on that. Yeah, you are doing good job. So just
Ma'am, one thing I want to know, do you suggest any online platform where we get like, so because we require a big GPU to run the code, na? So we get help and they provide us at free of cost. Do you suggest anything?
I am not sure of anything like that which provide large set of data for free of course. If I come to know, I can let Teresa, Dr. Jennifer, I'll let her
Yeah,
know.
ma'am, I sent a LinkedIn request to you, na? I
Oh,
tried to
okay.
connect with you.
I can let you know.
Yeah, ma'am,
Sure.
definitely.
Yeah.
Okay, ma'am, thank you so much for your wonderful help.
Bye. Yeah. Thank you everyone. Have a good day.
Thank you, ma'am. Thank you for taking the time to clarify all their doubts and inquiries.
Thank you. Thank you.
Thank you, ma'am. Have a good night.
Yeah. Bye.
Bye-bye. The feedback link is posted in the chat box. Participants kindly fill the form. We also thank all the participants for actively involving in both the sessions. Let us meet again tomorrow at 6 p.m. sharp. Thank you all.
Feedback link, please.
Ma'am, it's posted. It's posted in the chat box.
No, ma'am.
Oh, ma'am, it is not shared.
Ma'am, we
The chat
didn't
box,
receive the feedback link yet.
ma'am, the link is not posted.
Ma'am, feedback link, please.
It's posted now. Can you all see the link?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Thank you.
Thank you.